Hello there, everyone. My name is Prabhasha, and I'm a part of Passionate Minds. And today I'm going to be teaching to you SCH3U, or Grade 11 Chemistry. And I'm going to be going over the second lecture in my course, which focuses primarily on the atomic theory, the periodic table, and other related items. Alright. So going over the atomic models over time, the model has changed a lot. It looked like a billiard ball at first, and now it is commonly used Bohr model. It's very important to understand the different models that have been used over time to see how the atomic model has improved and changed and updated as well. The model will continuously change as new information is found and added into the future. Taking a quick look at the diagram here, we have the Bohr model, and neutrally charged neutrons are going to be located in the nucleus as well as positively charged protons, and orbiting the nucleus are going to be negatively charged electrons. Now, Democritus was the very first philosopher who asked the question, could matter be divided into smaller and smaller pieces forever, or was there a limit to the number of times a piece of matter could be divided? He was basically asking, was matter finite or infinite? Thomas was another philosopher who had the theory that matter could not be infinitely divided into smaller and smaller pieces forever. This meant that the smallest possible piece could be obtained, i.e., it was indivisible. He named this smallest piece of matter atoms, which the word atom comes from. Aristotle was another philosopher who completely rejected the idea of atoms and said that earth, water, fire, and air were the four elements that held Earth together, and this became the running theory for almost 2,000 years. This was not questioned for a very long time. It was only until another scientist, Dalton, came up with a newer model of the atom in 1803 that things changed up. Now he had the theory that all elements are made up of atoms, and this meant that atoms are indivisible and indestructible. He also said that atoms of the same element were exactly alike, and atoms of different elements were different. Compounds were also made by joining atoms of two or more elements. Alright, now Thomson in 1897 theorized that atoms are made of even smaller particles, electrons. This meant that atoms are positively charged and negatively charged electrons are around it, kind of like chocolate chips inside a cookie. He concluded that the negative charges came from within an atom and smaller particles than an atom had to exist. He also, like I said, identified what are now known as electrons and theorized that there are positive charges in an atom, but he couldn't prove it. This meant his model right here just shows that positively charged matter is just all around the atom, and electrons are just around, like the atom is positively charged, and electrons are just around it, like chocolate chips in a cookie. Now, Rutherford in 1908 carried out the gold foil experiment, where he fired a stream of positively charged particles into a gold foil. Now, most of these charged particles went through, however, some bounced away. This indicated that atoms are not positively charged as most went through. If atoms were positively charged, the gold foil's positively charged atoms would have made it so that all of the stream of particles that were shot would have just bounced away, because like charges repel like charges. If you take a magnet and put it against another magnet that are the same poles, like north-north against south-south, then they're going to bounce away. It's just not going to be able to be attracted to each other. This basically meant that atoms have a small dense center that is positively charged, the nucleus, and all of the atoms that are positively charged lie in the nucleus, and electrons are just scattered around the atom's edge. In 1913, Niels Bohr created another model, just updated on the Rutherford, and this indicated that electrons move in specific orbits around the nucleus, on energy levels that are located at certain distances around the nucleus. This is what you can see here, where orbits are just located at exact places, and electrons are just going to be located within this orbit. The most recent model is the wave model, and this model indicates that electrons actually do not move in a definite path like planets around the sun or in an orbit. This means that it's impossible to determine the exact location of an electron. You can see the wave diagram here, and I'll be showing it to you in the next slide as well. But basically, they're just in a wide, they're in a wider range than what Bohr had in his diagram. So the electron cloud is basically the space where the electrons are most likely to be found. This is what is indicated in the wave diagram. This means that electrons are actually not moving around in random patterns, but the location depends on how much energy electrons have. So the lower energy electrons are going to be closer to the nucleus, and higher energy electrons are actually going to be found in more energy levels that are further away from the atom. So higher energy electrons are just going to be located in orbits that are further away, and lower energy electrons are found closer to the nucleus. Alright. Now looking at the atoms and the composition. Elements can be identified by the mass number and atomic number, both of which are located on the periodic table for every element. The mass number is usually rounded to the nearest whole number. So if we take a look at sodium, it is rounded to 23 rather than 22.99. The atomic number is going to be the number of protons and the number of electrons in a neutral element. Keyword neutral. And if you subtract the mass number by the atomic number, you get the number of neutrons in the element. So taking a quick look at sodium, it has an atomic number of 11. This means that the number of electrons and the number of protons are going to be 11 for the element. The mass number is 23, and you subtract that by the atomic number, you get the number of neutrons, which is going to be 12. This means that sodium has 12 neutrons, 11 electrons, and 11 protons. Doing a couple more examples, we can take a look at calcium, which has an atomic number of 20, which means that the number of protons and electrons are going to be 20. You take the mass number, about 40, subtract that by 20, and you get the number of neutrons, which is going to be 20. So the number of neutrons, electrons, and protons are all going to be the same for calcium, all are 20. Now, we take a look at lithium, another element. It has an atomic number of 3, which means that the number of protons and electrons is going to be 3 for this element. You take the mass number, 6.9, you can round that up to 7, subtract that by the atomic number, which is 3, and you get the number of neutrons, which is going to be 4. Now, hydrogen. Hydrogen is a little interesting because it has an atomic number and a mass number of about 1. This means that the number of protons and the number of electrons is going to be 1 due to the atomic number, but if you subtract the mass number by the atomic number, you get 0. This means that hydrogen in its neutral form has no neutrons. Alright. Finally, we'll take a look at arsenic, a bit bigger of an element. It has an atomic number of 33, which means that the number of protons and electrons is going to be 33. Now you take the mass number, which is about 75, and subtract that by 33, you get 42, which means that the number of neutrons is going to be 42. Perfect. Now, Bohr-Rutherford diagrams. To draw one of these, you have to know the number of electrons, protons, and neutrons present in each element. The shells are filled with 2, 8, 8, and then 18 electrons per shell. 2 in the first, 8 in the second, 8 in the third shell, 18 in the fourth, and so forth. You're usually not going to do more than 4 shells for a Bohr diagram. You write in the number of protons and neutrons inside the center circle, and then you draw the electrons around the shell. We take a look at calcium as 2 electrons in the first shell, 8 electrons in the second shell, 8 electrons in the third shell, so that's 8, 8, 2, that's 18, and then you have 2 electrons in the outermost shell, which means that it has 20 electrons. We take a look at this element right here. It's not labeled, but we can take a look at the information we have provided and come up with a potential element for it. It has 2 electrons in the first shell and 4 electrons in its valence shell, and it has 6 neutrons and 6 protons. You add these two up together, you get mass number of 12, you have a atomic number of 6, and you'll learn this on later as you do more chemistry, but this is the element carbon. Alright, just taking a look at fluorine. It has 2 electrons in its first shell and then 7 electrons in its valence shell, which gives you 9 total electrons. You have 9 protons as well, which means that the atomic number is going to be 9. 10 neutrons, add them up together, you get the mass number, which is 19. Alright. Now, when we're looking at the isotopes, isotopes are the same element, but a different number of neutrons within the element. This means that the mass number is going to change, which is why mass numbers are usually not whole numbers, as you see on the periodic table. To give you guys a quick example, sulfur has a mass number of 32.1, and it has the isotope of 32s and 33s. Take a look at hydrogen. It's also actually not exactly 1. This is because it has the isotopes of 2H, which is deuterium, and 3H, which is tritium. 2H has 1 neutron, 3H has 2 neutrons. But these are both very rare, so this is why 1H, or hydrogen, is most abundant. To get isotopes average, you just take the mass number and divide it by the atomic mass. This is how you get the average of all the isotopes. Basically, you look at chlorine, which has an atomic mass of 35.5. It consists of 75.53% of 35Cl and 24.47% of 37Cl. These two numbers right here indicate the isotopic abundance of a particular element. This is going to be seen a bit more as we look at the average atomic mass, which is the average of the masses of all of the element's isotopes. So, to give you guys an example, carbon has an average atomic mass, or U, of 12.01, and this indicates that it has a 98.89% abundance of 12 carbon and a 1.11% abundance of 13 carbon. To calculate the average atomic mass, we have to use formula as shown below. So you take the abundance of an isotope, isotope 1, for example, you multiply that by the atomic mass of isotope 1, and then you add the abundance of isotope 2 multiplied by the atomic mass of isotope 2, and then you add the abundance of isotope 3, if there is one, multiplied by the atomic mass of isotope 3, and so on and so forth. To give you guys an example, let's look at argon. Argon has 3 isotopes, argon 40, argon 36, and argon 38. The average atomic mass is the abundance of the first isotope, Ar40, 0.99, multiplied by the atomic mass, first isotope, 39.962, and then you add the abundance of the second isotope, 0.00337, multiplied by the atomic mass of the second isotope. You take the abundance of the third isotope, multiplied by the atomic mass of the third isotope, and then you get the average atomic mass, which is normally indicated on a periodic table. Taking a look at chlorine, another element, and its isotopes, it has 2 main ones. The average atomic mass is going to be the abundance of the first one multiplied by the atomic mass of the first one, and you add that with the abundance of the second isotope multiplied by the atomic mass of the second isotope to give you about 35.4, 35.5. Now, if you're looking for the isotopic abundance, but you already have the average atomic mass, the atomic mass, and the 2 elements, this is how you figure out the isotopic abundance of a couple elements. Basically, you have to have the average atomic mass already, and you take this and you do the same formula. So 10.81, the average atomic mass, is going to be X, which is the isotopic abundance of element of the first isotope, multiplied by the atomic mass of the first isotope, and then you add 1 minus X. This is the second isotope multiplied by the atomic mass of the second isotope. It is 1 minus X because for these two particular isotopic abundances, both of them add up to 100%, or to 1. So you take X, which is going to be a decimal place, and you take 1 minus X, which is going to give you the value of the second isotopic abundance. So 10.81 equals 10.01x minus 11.01x plus 11.01. You move these two to the right, which gives you x, or 1x, and you move this to the right side, which gives you 0.2. So x is 0.2, 1 minus x is going to be 0.8. This means that the isotopic abundance of boron 10 is going to be 20%, and boron 11 is going to be 80%. Taking a look at potassium, it has an average atomic mass of 39.1. 39.1, the average atomic mass, is going to be the isotopic abundance of the first isotope, K39, multiplied by the atomic mass of the first isotope, 39. And it's going to be plus the second isotope, 1 minus x, the isotopic abundance is indicated here, and multiplied by the atomic mass, the second isotope indicated there. So 39.1 is going to be 39.0 minus 41.0 plus 41.0. So you move these two to the right, 2x is going to be, move these two to the left, sorry, and move this to the right. 2x is going to be 1.9. This means that x is going to be 0.95. And 1 minus x is actually going to be 0.5. So, the isotopic abundance of K39 is 95%, K41 is 5%. Now, the types of elements that you can find. There are three main ones: metals, metalloids, and nonmetals. Just going over some basic properties of each three. Metals are generally malleable, which means that they can be shaped into many different things. They're also ductile, which means they're able to be pulled and drawn out. They're lustrous, which means that they're shiny, and they're good conductors. They have high densities and high boiling points, and with water, they're going to form strong bases, which means that they're basic in nature. Metalloids contain characteristics of both metals and nonmetals, and nonmetals are dull, they're weak conductors, they're brittle, which means that they break very easily, and they generally form acids with water, meaning that they're acidic by nature. Now we look at a periodic table. Metals are going to be pretty much everything up to here. Metalloids, it's a staircase. It's not indicated here, but it's boron, silicon, phosphorus. It's a staircase, yeah. So you got boron, silicon, germanium, arsenic, not phosphorus. Phosphorus is a nonmetal. Arsenic, antimony, tellurium, palladium, and acetane. You'll see this later on as I talk a bit more about elements, but it basically is a staircase going from At to Pd to, polonium to Po to Te to Sb to As to Ge to Si to B. And you got all these different groups that are located on the periodic table as well. You have alkali metals, which are the first group, alkaline earth metals, the second group, transition metals, which are located here, halogens, which are the seventh group, and noble gases, which are the eighth group. Now, talking a bit more about groups and periods in the periodic table, groups are going to be the vertical columns along a periodic table. Group 1 is alkali metals, not hydrogen. Group 2 is alkaline earth metals, which is the second group. This is group 3, this is group 4, this is group 5, group 6. Group 7 is halogens, and then group 8 are noble gases. Periods are basically rows along the periodic table. So this is going to be the first period, the second period, third period, fourth period, fifth period, and these ones are more indicated by the number of shells that are located within the element. Groups are indicative of the number of electrons that are located in the valence shell. So this one has 1 electron in its valence shell, all of the elements, 2 electrons, 3 electrons, 4 electrons, 5, 6, 7, and a full octet for the noble gases. Transition metals are a bit different because they don't carry the same properties as these four do. Taking a look again at the groups, alkali metals, there's 1 electron in the outer shell. They're all very reactive, and the reactivity increases as you go down the periodic table, and they react in water and air, are pretty conductive. They're shiny, which means they have luster, and they're ductile. Alright, now alkali earth metals, they have 2 electrons in their outer shell. They're less reactive than alkali metals, and their reactivity increases like alkali metals as you go down the periodic table. When looking at group 7, halogens, they have 7 electrons in their outer shell. Their reactivity increases as you go up the periodic table, so therefore fluorine's the most reactive, like I said. They're all nonmetals, and they all form acids with water, and salts with metals. Now, the final group, group 8, are noble gases. They all have a full outer shell, meaning that they have 8 electrons in their valence shell. They're all unreactive due to the full octet of electrons that they have, and they are all gases at standard temperature and pressure. Now, STP is for 0 degrees Celsius or 273 Kelvin, and it's 1 atmospheric pressure, but this is something you don't need to worry about right now. It's just they're all gases at STP. All right. Now, looking a little bit more into definitions, electronegativity is the ability for an atom to attract electrons to itself. This increases as you go right on the periodic table and as you go up the periodic table. Electron affinity also is the change in energy as an electron is added to a neutral atom to make it negative. This also increases as you go right on the periodic table and as you go up the table. Ionization energy is energy required to remove an electron from itself. This increases as you go up the periodic table and as you go right. And finally, atomic radius is half of the distance between two equivalent atoms. This increases as you go down the periodic table and as you go left across the periodic table. Taking a look at each of these diagrams right here, they're pretty indicative on what they represent. The atomic radius increases as you go down and decreases as you go right, so increases as you go left. Therefore, francium is going to have the largest atomic radius. We take a look at electronegativity. It increases as you go right and decreases as you go down, so increases as you go up. And since all the noble gases are full octet, they can't attract any electrons. Therefore, fluorine is going to have the highest electronegativity. Electron affinity and ionization energy both increase as you go up and as you go right across the periodic table. I'll just take a little minute here just to let you guys look at all these different charts and what they represent. All right. Oops, there we go. So, ionization energy, electronegativity, electron affinity, they all increase as you go right and as you go up. Atomic radius is the only one that increases as you go left and as you go down. Yeah, let's take a look at ions. Now, when an atom has gained or lost electrons, protons and neutrons can't be lost as they're located in the nucleus. This is how an ion is formed. If an atom gains an electron, it becomes negatively charged, an anion. To give you guys a quick example, chlorine has a strong pull for electrons as it has 7 electrons in its valence shell, 17 electrons total, and it wants to fill this up, so it might pull an electron and become Cl-, which means that has 8 electrons in its valence shell, 18 total. The charge also becomes -1, it's not neutral anymore. If an atom loses an electron or electrons, it becomes positively charged, a cation. To give you another example, calcium has only 2 electrons in its valence shell, 20 total, and since it wants to lose both of these to have a full outer shell, it might lose both electrons to become Ca2+. This means that this shell is going to have 0, so it's going to go down to its previous shell, which has 8 electrons in its valence, and it has 18 total. Cations are positively charged and they form when electrons are removed. The atomic radius is going to decrease because since there are less electrons in the atom, there's going to be a stronger pull from the remaining electrons to the nucleus, meaning that the radius will shrink. And if there's only 1 electron in the valence shell, the atom is going to go down in energy level, meaning it's going to get smaller. Now, for anions, they're negatively charged and they form when electrons are added. The atomic radius is going to increase in this situation because electrons are going to feel less attraction from the nucleus and more electron-electron repulsion, because since electrons are all negatively charged, they're going to repel each other and there's going to be less electron attraction from the nucleus. Alright, now looking at reactivity, metals reactivity increases as you move down the periodic table, so down groups, as large atoms react quicker than small metal atoms. However, when we're looking at nonmetals, so anything after the metalloids, after that staircase, the reactivity is going to decrease as you move down. the periodic table, as smaller non-metal atoms are able to react quicker than large non-metal atoms. So the reactivity actually increases as you move up. Alright. Now looking at electronegativity, a very important topic. This is the ability for an atom to attract electrons to itself. Fluorine has the highest electronegativity, or En, as I said before. There are three types of intermolecular bonds, bonds that can form between different molecules that can be identified by the differences in the En. Covalent, polar covalent, and ionic. Covalent bonds are when the difference in electronegativity is between 0.0 and 0.5. Polar covalent is when the difference is between 0.5 and 1.7, and ionic is either when the difference is over 1.7, or the bond is between a non-metal and a metal. This means that for non-metal and a metal, if the electronegativity is below 1.7, it is still considered ionic. And an example of this is lithium iodide, LiI. The electronegativity of lithium is 1.0 and iodide is 2.5. So when you calculate the difference and see that it is 1.5, technically this should be polar covalent because it's between the threshold for polar covalent, but since lithium is a metal, the bond is ionic. This is a chart of electronegativity. Alkali metals generally have the lowest ones, and then alkali earth have low ones as well. And as you move to the right, halogens right here have high electronegativity, and we don't look at noble gases because they won't be able to react. Alright, ionic bonding. Ionic bonding forms when a metal and a non-metal combine to form a bond. The metal loses one or more electrons, forming a positive ion. The non-metal gains one or more electrons, forming a negative ion. The bond forms between positive and negative ions, and both the metal and the non-metal want to have a full octet shell, whether that means losing an electron or gaining an electron. So when we're taking a look at sodium fluoride, NaF, here, sodium has 1 electron in its valence shell, and fluorine has 7. Sodium doesn't want this electron, and fluorine wants it, so this electron completely transfers over to fluorine, creating Na positive, fluorine negatively charged, as you can see by the electron transfer here. Alright, now looking at covalent bonding. Covalent bonding occurs when electrons are shared between two atoms, usually nonmetals and a metalloid, or nonmetals and nonmetals. Both of these atoms acquire electrons to reach a full octet shell. This means that electrons are going to be shared between the two. Single bonds are indicated by 1 dash, double bonds by 2 dashes, and triple bonds by 3 dashes. The bond represents one pair of electrons that are being shared, or 2 electrons. So, taking a quick example from HCl, hydrogen has 1 electron, chlorine has 7, but since they both want to have a full octet, or in hydrogen's case, no octet, they share the electrons. Now, when we look at diatomic molecules, Hoberfinkel ones, this is something it is important to memorize. Hydrogen, oxygen, bromine, fluorine, iodide, nitrogen, chlorine. These are all molecules that are composed of 2 atoms that are identical. So you look at O2 in its regular state, in its gaseous state, or N2 in its gaseous state. They're always going to be N2, O2, H2, Br2, and so on and so forth, when you're just talking about them by themselves. Right. Now, looking at polar covalent molecules, this is when one end is positively charged and the other end is negatively charged. So, for example, HCl, H2O, and the difference in electronegativity is going to be greater than 0.5. Taking a quick look at hydrogen chloride, Cl is very electronegative compared to hydrogen. This means that this chlorine molecule wants to have both of those electrons that are being shared. So the electron pull is going to be higher here, making this more negatively charged. And since there are no electrons around hydrogen, the sharing is going to be pulling towards chlorine. Hydrogen is going to be positively charged. Now, when we're looking at non-polar covalent molecules, this means that there's neither a positive nor a negative pull. The difference in electronegativity is going to be less than 0.5. This is usually between diatomic molecules, like the Hoberfinkels, but can also work between alkanes, so like methane, CH4, where hydrogen has electronegativity of 2.1 and carbon has 2.5, the difference is going to be 0.4, so it is nonpolar covalent. Usually when it's nonpolar covalent, it's going to be symmetrical. So since in methane or CH4, they're all pulling towards the center, it is symmetrical because carbon is more electronegative than the four hydrogens. Alright, now just taking a quick look at these three molecules. Methane has four single bonds. So two electrons are being shared here, 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 and here. This means that carbon has a full octet, and all of these have two electrons in their valence shell as well. When we take a look at ethane, a molecule with a double bond, four electrons are being shared here, and another two here, and another two here, and two here. This means both of these have 8 electrons as well, and the four hydrogens have 2 electrons in their valence shell. And then we take a look at another molecule, propane. It has 2 electrons being shared in each of the bonds between the C's and the hydrogens, and between the carbons as well. And to finish off, just a chart of ionic compounds versus covalent compounds. Ionic compounds are between non-metal and a metal. They transfer electrons from the metal to the non-metal due to the electronegativity difference. They are going to be positive and negative charges due to the electron transfer. We don't need to worry about the Greek prefixes or the Roman numerals. They're going to be solid at room temperature at 25 degrees Celsius. This is also STP. They're going to have high melting and high boiling points, and they're also going to have a high attraction between the particles. Now, when we're taking a look at covalent compounds, they're between a non-metal and a non-metal, or a non-metal and a metalloid. There's going to be electron sharing, not transfer, because the electronegativity difference is going to be less than 1.7. There's going to be no charges due to the electrons being shared. They're going to be solid, potentially, liquid potentially, or even gaseous at room temperature, depending on the molecule. There's also going to be low melting and low boiling points, and weak attraction is going to be occurring between the molecules. And this caps off today's lecture. Tune in next time for lecture 3, where we're going to be focusing a bit more on the second unit. And that's it for today.